Hey everybody, thanks so much for being here today for the virtual OpML 2020. My name is John Zedlewski, I'm from NVIDIA, and I'll be talking about how RAPIDS lets you do GPU accelerated data science. So we probably want to start by setting the scene with why do we even care about GPU acceleration for data science and how does it make a difference? After going over that background, we'll really dig into the RAPIDS stack, all the different pieces of it, how it lets you do ETL and machine learning. And then for this audience in particular, I want to make sure we really talk a lot about how we handled scaling up. So we all know that one GPU is pretty fast, but we want to make sure you can tackle huge problems by combining Dask, UCX, and other modern networking technologies to allow you to take advantage of a whole cluster of GPUs. We'll do a deep dive into a benchmark called TPCXBB and how we handled it with RAPIDS. And then finally, I want to leave with a couple notes on how you can start playing around with RAPIDS and give us feedback. So first, why do we care about accelerating data science to GPUs anyways? Well, I think it's no secret that we don't live in a single-threaded world anymore, where you can just count on single-threaded CPU performance growing year after year. However, aggregate GPU performance has been growing at an incredible rate. So the gap between what you can do with a single-threaded CPU-based library and a GPU-based library gets bigger and bigger every year. And we want to really take advantage of that. When you have a GPU nowadays, like with the newest A100 GPUs that come from NVIDIA, the amount of compute power you can get in one spot is pretty incredible. You're talking about 20 teraflops of general purpose compute power and 1.6 terabytes a second of memory bandwidth, which is sort of mind-boggling. You also get a machine with a pretty complex topology. So here, between any two GPUs in this node, you have incredibly high-speed NVLink interconnect, which are 600 gigabytes a second of communication bandwidth between two GPUs. However, when you go from one node to another, you may go over either a PCI switch, or maybe you have to go out to the network and do a hop through Infiniband or through Ethernet. We want to really take advantage of technologies that are going to allow you to keep as much compute as possible down here where things are fast and not spend your time being bottlenecked by trips up through here. When we talk about GPU accelerated data science, it's worth thinking about data science pretty broadly. So we don't just mean deep learning, where GPUs already have a huge footprint and most practitioners are familiar with the value of a GPU. Same things that make GPUs good at deep learning, like really fast linear algebra and huge memory bandwidth, also make them really good at traditional machine learning, whether it's linear regression models, clustering, or tree-based models like gradient boosted decision trees. And also we can take many of those same properties and use it to improve our performance in traditional analytics as well, whether you're just doing grouping and aggregation on huge data sets or doing more complex ETL and transformation. It's really important to make sure you're approaching the end-to-end problem, not just focusing on the machine learning component too. So when we went to build a product to help data scientists get their jobs done faster, it was obvious pretty quickly that there's really two huge communities to address. You've got the Python data ecosystem, things like Pandas, scikit-learn, and NumPy, which is huge and growing and goes in everything from desktops to servers and clusters. And you have the Apache Spark ecosystem. We decided we want to build RAPIDS in a way that we have a core of C++ and CUDA code that can easily have different front ends attached to it. So here we built both the Python data front end and an Apache Spark front end. Apache Spark has been getting a lot of traction on GPUs, especially with the release of Apache Spark 3.0. We won't be talking as much about that side today, and instead we're going to focus primarily on the Python data side of RAPIDS, which has been out longer and is the focus of the group I work with. Now, when we talk about Python data, it's not just Pandas and scikit-learn. There's this huge community of things like Dask and NumPy and all the deep learning frameworks you know. So RAPIDS really had to be built to take advantage of that whole community and to interoperate with it rather than trying to compete. So when we talk about RAPIDS, what is it? Maybe some people are familiar with it already, but it's worth kind of starting from the basics here. And really, the basics start from looking at the familiar Python data ecosystem on CPU. So on a CPU, you might use Pandas for analytics, then feed into some scikit-learn machine learning, do some graph analytics in NetworkX, and maybe apply some deep learning models, maybe followed up with some visualization like matplotlib. We want you to do the exact same thing on GPU with parallel libraries. So instead of using Pandas on CPU, you switch to cuDF on GPU. You go from scikit-learn to KUMAL or NetworkX to cuGraph. All of these are built to have APIs that mirror their CPU-based counterparts, so you really don't have to learn much new stuff. One of the most important points in RAPIDS is that we use a very common data format for all of the libraries that plug into it based on Apache Arrow. This means that it's really easy to interoperate between these libraries and move data between them without having to serialize to a different format, without having to write to disk or even just go to the CPU memory. So we were motivated in a lot of this by looking at the pain that several of us went through back in the big data, Hadoop, the early days of big data, when Hadoop was dominating, and when you could have a really fast operation, but it could easily be bottlenecked on the amount of time taken to write back to HDFS and read back from HDFS. Spark alleviated a lot of this bottlenecks on the CPU cluster side. But when people started moving machine learning, training, and other operations to GPUs, they found there's kind of a parallel problem there. Instead of writing to disk, instead, between each of these fast operations, you often have to persist back to some standardized format like Parquet, write it out into host memory, and then read it back in a GPU. We wanted to get rid of that completely. We want to eliminate all of these unnecessary conversions that go over the PCI bus between the CPU and GPU. Part of the way we did that was by adopting Apache Arrow. Apache Arrow is an open standard that's already deployed in a lot of big data infrastructure that allows libraries to share a common format for columnar data representation in memory. It means that you can go between two libraries with a simple in-memory structure rather than having to write everything onto disk. RAPIDS adopts the Arrow format and brings it down to GPU memory so we can interoperate the same way on GPU and get this much nicer picture where we've eliminated all of these CPU reads and writes and gotten the high performance that we're looking for. So let's dig in a little bit deeper to some of the specific libraries that make up RAPIDS. We won't have time in this short talk to go into all the details. I really hope you check out the rapids.ai site. But just as a quick overview, it's really worth starting with cuDF because cuDF we think of as the backbone of RAPIDS in many ways because it enables you to do ETL and provides a data representation. If you've ever written pandas code, this code over here on the right in Python might look really similar. Say load a CSV, do some string encodings from character over to integers, and then convert to a real integer. This stuff the data scientists do all day long when loading and transforming data. The difference here is that we're using cuDF and storing the data frame entirely in GPU memory, and all these operations, including the string operations, are all done in GPU memory too. So you can have that really nice, easy Python API, but have all your operations done transparently on GPU with much higher performance. And it is a lot higher performance. For something as simple as a merge of two data frames, you get up to a 970x improvement when moving from pandas to cuDF. Things like sorts and group bys are the backbones of every transform and ETL operation that I know get 300x speedups or more. These are not little niche obscure operations that get faster. This is the stuff that data scientists and data engineers do all day long, really. But of course, before you can get the data there to transform it, you've got to load it. So cuDF includes the cuIO sublibrary, which enables GPU-based data loading. Here, you load the data and do all the decoding and translation work you need on the GPU itself. So operations like reading a CSV that for large data sets can become a bottleneck easily are immediately sped up by a huge factor. This is because actually the time that Pandas spends doing the translation from CSV to a data frame is really a lot of compute time in a single threaded model. By just moving that all onto the GPU, we were able to get a huge speed up with a well-written decoder. We can do the same thing for Parquet, Orc, JSON, Avro, a lot of different big data set formats. But once you've loaded that data, you often want to pipe it into some machine learning package. That might be a deep learning package like Python, like PyTorch, TensorFlow, or MXNet. And we didn't want to go about rewriting or competing with any of those. They all have great GPU support already. So instead, we're leveraging open standards from the Python community called DLPack and CUDA array interface to make sure that when you load data with RAPIDS, it can be immediately fed into any of these libraries that you have downstream without having to round trip through some serialization format, without having to round trip through CPU memory. DLPack is really simple. It's just an expression of how your data in a tensor is laid out in memory. It can support memory on CPU or GPU, and it's something that was really core to the way we made RAPIDS interoperate with all of these deep learning libraries. It has native support in all of these deep learning libraries, and support is coming to TensorFlow in an upcoming release. There's already a PR in flight for it. CUDA array interface is an even easier Pythonic wrapper over the same idea. We support both, and this allows you to really transparently move Python data frames in these libraries. Now, if you're not using deep learning for your pipeline, you're using traditional machine learning, you might be using scikit-learn today. We built KUMAL to be a direct drop-in replacement for scikit-learn. So if you have code that looks something like this, like a classic data set build up and then a clustering model being built on it and then graphed, translating this from the current CPU code you see here to GPU code is as easy as making these changes you see here in red. Really, it's the exact same APIs, and we're doing everything we can to expand the KUMAL API continually to support more and more of scikit-learn. What do we support today? Well, we went for kind of the greatest hits of machine learning, and we keep expanding this list. In particular, we keep expanding it based on user and community feedback. So if you have additional models you'd like to see, please give us feedback. We already cover a lot of popular classification and regression models. Clustering, K-means is very popular there, as is dbScan. And we've seen a lot of interest in using the dimensionality reduction methods like UMAP and tsne. These can get really slow on CPU, and they're typically used for large data sets or visualization or pre-processing. So you typically have a ton of data and you can really get bogged down. We can speed those up by huge factors. We're increasingly adding more pre-processing utilities, time series, and a bunch of other nice quality of life features too. So definitely check out the list on GitHub. How much faster is KUMAL? Well, it goes anywhere up to, say, 700x or greater for a support vector machine model with RBF kernels. It might be 100x for a large data set with UMAP or with PCA, for instance. Some of the less compute-intensive models, maybe you only get a 6x speed up with some smaller data sets. But the rule is pretty simple, that as your model gets more compute-intensive and your data set gets larger, you're going to see a greater and greater speed up from going to KUMAL. We're also working with other packages outside of KUMAL, like XGBoost, to make sure they play well with the GPU data community. So for instance, we've contributed code to XGBoost to allow it to do zero-copy import from cuDF, CuPy, Numba, or PyTorch arrays. So basically, XGBoost can take advantage of that same DL-pack-based ecosystem that RAPIDS is able to take advantage of. And XGBoost already has great and constantly improving GPU acceleration. So here for some data sets, you can see speedups of up to 17 or 18x when comparing a single GPU against a 40-core, pretty beefy CPU-based node. And it varies from data set to data set, but it's continually improving on GPU. Increasingly, to make sure people can get end-to-end pipelines on GPU, we're also expanding support for more inference pipelines. Once people build up large decision tree-based models, whether it's XGBoost or a random forest, they can find that scoring becomes a real problem, especially if you're doing something like rescoring all of the examples in a large data set nightly. We've heard a lot of customers say that's become a major pain point for them. So we built the Forest Inference library to accelerate that sort of inference on GPUs as well. You can see again, when comparing a single GPU against 40 cores, you can get massive speedups across a lot of data sets from 23x to 36x. And this again is translating a many node, like cluster-wide problem into something that you can do for your huge data set on a single GPU-based node. Increasingly, we're seeing RAPIDS used within hyperparameter optimization frameworks too. Within a hyperparameter optimization problem, or HPO, you're typically running hundreds or more of variants of a model. So that model speed up really gets multiplied a lot. This particular example you can find more about on rapids.ai/HPO. But here, for a random forest hyperparameter optimization model, we got about a 24x speed up from converting to RAPIDS. One critical thing is that when we integrate with cloud-based HPO solutions, you can then get your problem done faster, and that means you shut down your cloud resources much sooner. And that translates directly to a huge cost reduction. So here, the GPU-based instances were a bit more expensive. They're about 3 times more expensive per instance. But by getting a 24x speed up, you end up with a huge cost reduction. This costs 7 times less to do on RAPIDS in the cloud than it costs to do in scikit-learn in the cloud. It translates directly to the bottom line in that case. We're increasingly building up more and more of the cuGraph library as well, which is a mirror to the NetworkX CPU-based library. It has that nice Python-based ease of use, covers all of the major, most popular graph analytics algorithms like PageRank or Louvain, and delivers just massive speedups when compared to NetworkX in particular, but really is a best-of-breed performance for graph analytics. We've tons more libraries rolling out all the time. I hope you check out rapids.ai and see them in more detail. But I want to make sure we have a little time to talk about how we're handling distributed compute. Because RAPIDS lets you scale up a ton with a single GPU even and tackle much bigger problems and faster. But there's always going to be a limit to how much you can tackle with a single CPU, a single GPU, or a single node. So just as the Python data ecosystem uses Dask to scale out, we've built a scale out system built on Dask and additional technologies with RAPIDS. So you can scale across a cluster or just across multiple GPUs on a single node. There we're leveraging Dask heavily and also a technology called OpenUCX I'll talk more about. So why Dask? Well, it's really popular within the Python data community for being super easy to use. It mirrors existing APIs, much like RAPIDS does, and it really gives you that feel of single node programming, but distributed across a cluster. It's also super easy to deploy. Whether you have Kubernetes or a cloud provider, or Yarn, or an HPC solution, you can almost certainly run Dask on top of it. You don't have to rip out an existing cluster scheduler, or you can just run it on a desktop or workstation, or even on a laptop really easily. But as you increase the speed of compute by using more and more GPU horsepower, it's very easy to end up with communications bottlenecks if you're going over a slow link. So we've integrated deeply with OpenUCX, which is a technology that provides a consistent wrapper across a wide range of networking technologies. This allows you to take advantage of NVLink for fast intra-node communications, Infiniband or TCP over Ethernet, whatever you have connecting between nodes. And it allows you to just use a single programming interface that will be topology aware and intelligently route messages over the fastest possible channel. You can see this can make a huge difference in benchmarks. So for a realistic merge, we can go from about a 2 gigabyte per second bandwidth of transfer to about 37 gigabytes once we've gone from just doing a simple TCP-based approach to really using optimized UCX over Infiniband NVLink. So by deploying Infiniband NVLink widely and then layering UCX on top of it, we're able to get much closer to the maximum theoretical throughputs for these models. You can see right away, if you're familiar with Dask plots, that without UCX, this is a series of timelines of workers and what they're doing. The workers with no UCX spend all the time in this red state, which means waiting communications. Once you move away from UCX, you get rid of that red. So we've been using this really heavily within the TPC-XBB benchmark. TPC-XBB is a big data benchmark from the TPC consortium, which has been largely done with Hadoop technologies like Hive or Spark, like Spark SQL. We wanted to demonstrate that we can really bring that all onto the GPU world and take advantage of these end-to-end pipelines. So we've been doing TPC-XBB at both the 1 terabyte and 2 terabyte scale factors. It's a size configurable benchmark, and I've gotten some pretty incredible speedups after porting the entire benchmark suite over RAPIDS. For a 10 terabyte problem, you can get about a 10x speedup over the best publicly available CPU solution. And when you account for cost of ownership of both of them, it's about 5x cheaper to do this performance-wise to do this in RAPIDS than on CPU. When you go to a smaller problem that can fit in a single node, you'll get more like a 40x cost of ownership reduction to get the same performance, or a 51x speed up. Really incredible progress. And one of the things we're excited about is that these are really beefy, complex queries that include not just machine learning, but also all kinds of data prep, aggregation, sectionization, things that big data engineers are doing all the time, both in machine learning pipelines and before them. So it's exercising really the whole system end to end. This is taking a huge amount of advantage in our latest versions of UCX, and it's really shown how much you can get out of a Dask-based scale-out solution, which I think is pretty exciting. Now, before we leave, I want to make sure I point you to some of the resources so you can get started and try out RAPIDS on your own. RAPIDS is totally open source. You can just go to rapids.ai and get started with either a Docker container or Conda installations, or you can just launch a Colab notebook right away. We have a lot of really useful walkthrough videos, but I especially want to call out the blog content. Many of the things that are shown in this deck, whether they're benchmarks, TPC-XBB, graph algorithms, and machine learning, have much more detailed blogs with rich technical content. So you can dive into those and see much more detail, and then try out the tutorial notebooks yourself. Please do give us feedback. We love to get issues on GitHub. We love for people to join the public Slack that we have and give feedback or just ask questions. We're really excited about the future of RAPIDS, and we hope that we can work together with the OpML community and everybody else scaling up their machine learning and ETL problems to really make lives of data scientists and data engineers better by making things much faster. Thanks a lot.